Hi, welcome to the Overture, or Lecture 0, Hi JAX, How's Life? So this is the first lecture of Hi JAX, in which we're going to get our first taste of JAX. The plan is basically to port an elementary cellular automaton simulator that was previously written using NumPy to run in JAX instead of NumPy. In doing so, we're going to get a first taste of JAX and some of the limitations of JAX array programming and what flexibility and speed improvements those limitations, conforming to those limitations, allows. You can follow along with this tutorial if you grab the starter code and from the GitHub repository and watch the instructions in the environment video. But let's get started. So first, let me just explain what an elementary cellular automaton is. So some of you might have seen Cellular Automata before, including Conway's famous Game of Life. We're going to be looking at a much simpler cellular automaton today. And it's basically a cellular automaton where the state is a one-dimensional array, so like this. And each cell in the state can be alive or dead or on or off. And we're going to indicate alive cells by coloring them in black. And then in order to evolve the state of this automaton, you can see in this animation, you look at groups of 3 cells together and then look at a corresponding rule in a lookup table that says whether with this combination of cells, whether the next cell should be alive or dead. And so you'll see, for example, here, when we see this combination, the rule says that the corresponding next cell should be alive. And then we look in the next state and we see that the corresponding cell is alive, along with a bunch of other cells. So we're going to look at an implementation of this kind of cellular automaton in NumPy. Let's get looking at that. So I'm in the Hi JAX repository, and you can access this repository on the course GitHub page. And just a reminder, you need to have the virtual environment active to run the code in this tutorial. So it's going to have JAX, NumPy, and all of the other necessary libraries installed. So inside this repository, there's code for all of the lectures, and today this is lecture 0, so we're going to look at the lecture 0 repository. And inside here, there is this elementary cellular automaton version 0, which uses NumPy. And so I'm first going to spend a little bit of time kind of explaining this code, because this is going to be the basis for porting this simulator to NumPy. From NumPy to JAX. It's a pretty short script. There's basically just this main function which sets things up and calls this simulator, plus doing some timing. So we're going to grab the time before and after running the simulator and then print out how long this took. And then we're going to print out the sort of the result, the history of the cellular automaton state, which gives us some pretty pictures. Although alternatively, you can configure it to save to an image rather than printing it out to the terminal. I'll explain a little bit more about that later. The real thing we're here for is this simulator code. And so I guess I should mention that I'm going to be using a few libraries here, and we're going to be using these more and more throughout the course. Some libraries I'm going to be using consistently are Tyro, which basically just allows to turn the main function's arguments into a command line interface. So for example, I should be able to Python ECA0 and then help, and it will say that all of these inputs that I have to the main function have been converted into command line arguments that I can use to decide each time I run the program what I want these variables to be. Another thing to look at is, which we'll see in a second, matplotlib, which is my terminal plotting library, which we'll be using for visualizations in this lecture and some of the other lectures. And another thing is we'll be looking at this JAX typing. So this is, even though JAX is in the name, this is just a generic typing library for arrays. And so one of the things this will allow us to do is sort of say what shape the sort of inputs and outputs of our functions are. And so back to the simulate function, this is going to be a function that's basically going to take a rule, which is going to be like a description, a specification of that lookup table from before. And it's going to do the simulation and return a result, which is going to say it's going to be a 2-dimensional array where the first dimension is going to be the number of steps. So this is like each generation of the cellular automaton. And the width is going to be how many states we have in total. And so before I talk through this code, let me show you this actually in action. So speaking of running with Tyro, we can run ECA0 just with the default argument, so rule 110, a width of 80, and a number of steps of 80, and we'll set it to print the image but not save an image, and we should see something like this. So let me scroll back up before we explain this. So basically it sort of prints out the rule and converts it to a lookup table, which is sort of represented here, and then it runs the simulation, tells us the time, and then it prints out the result of the simulation. So what we're seeing here is a terminal rendering of the sort of many generations of this rule going on. And so you can see in the first row, we've initialized the automaton to have mostly dead cells, but then one cell roughly in the middle of the width is on, marked in black there. And then in the next generation, there's 2 cells on, and then so on and so on. We apply the rules and we get this sort of kind of interesting behavior. One thing to note is that this simulator is set up to wrap around at the edges. And so this is actually why over here, when we get to the edge of the array and this cell is alive, that actually causes in the next generation this cell to be alive, and then the pattern kind of continues. And if we continued for a few more steps, if I said num steps, for example, to be 100, we would see that kind of continue. But yeah, information is kind of be flowing around, wrapping around the edges of the automaton. And that's something we're going to have to implement in the simulator with NumPy, and then again, port to JAX. How about we step through this code to see how this is actually calculated? So the first few steps are about determining the lookup table that is going to be used. And so the way that we specify lookup tables in elementary cellular automata is using Wolfram codes, which are basically using the binary representation of the rule number in order to say what the entries in this lookup table should be. So we've used the example of rule 110, and the first step of this code is to sort of make that rule into a NumPy integer, which is an unsigned integer with 8 bits, so between 0 and 255, but it's going to have 8 bits. And then you can see here I'm printing out that rule as a decimal and then also as a binary. And so that is what we end up with here. We end up with the rule 110, that's the decimal representation, the binary representation of which is 0110, 1110. And so you can see there, that's the binary representation. And so to convert that into a lookup table, the convention is to basically say that when the sort of 3 cells, when this neighborhood is in state alive, 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 or 111, then the first bit of the binary number is going to be the result next, so 0. And then when it's 110, then the next set is going to be the second cell of the binary representation, and so on. And so I think the Wikipedia page has a pretty good picture of this. Basically, you have, like what I said, when the cells are all on, you look at the first bit. When the cells are almost all on, you look at the next bit, and so on. This is a different rule, rule 30, so we have a slightly different entry here, but you can see that this binary representation is corresponding to the sort of 0, 0, 0, 1, 1, 1, 1, 0 in the next states. And so we've just implemented that here. How do we actually calculate this lookup table? So NumPy has this function unpackBits, which takes an unsigned 8-bit integer and converts it into an array of the binary digits like this. And I made sure to do this in bit order little to get the least significant bits first, the little bits, and that basically gives us the reverse of the usual representation. So this 0, 1, 1, 1, and then 0, 1, 1, 0 becomes the order of the array, reading it backwards. And I did that because then I want to enumerate through this in the opposite order. Instead of starting with 1, 1, 1, I want to start with 0, 0, 0 and read that into a lookup table. So how do I read it into this rule table? That's actually very simple. All that requires is to just use reshape, which is a method on any NumPy array that you can use to change the shape of the array. So we previously had this array which had just a single dimensional shape of size 8. And I'm reshaping that into a 3-dimensional array where the height, width, and depth, if you like, are all 2. So 2 by 2 by 2 array. And that basically is going to mean that in the position that was previously position 0, that's the 0th sort of, I guess, like layer of the array, and then the 0th row, and then the 0th column, and that's going to have the initial thing from this array, 0. And then the next 3, so on, we sort of go through. But the upshot of this is that I'm going to be able to index into this table with a particular combination of cell states, and it's going to give me the sort of the corresponding part of the binary representation of the rule. And so this code here, I think now should hopefully make sense. This is all about how we're representing this lookup table. Okay, the next step of the code is actually even much simpler. We're going to initialize a new NumPy array, which is going to be a uint8 array as well. I guess there's no particular reason this had to be uint8. We're only using it as basically a Boolean, but it's going to be an array with a particular width, which is our configured width that's come in as an argument here. And I'm going to initialize it as zeros of that shape width and this dtype NumPy uint8. And then I'm going to, that basically gives us a blank state array. And then I'm going to say the state should be in the middle somewhere, width over 2, rounding down. We should set that state to 1, so make that cell alive. And so after this combination of lines, this one here is just a type annotation for readability, this is going to give us what we want. This is going to give us a NumPy array that has all zeros and then 1 in the middle. And the final step, I guess, to make the magic happen, we need to put together this state with this lookup table and use this to generate the next state. That is going to be, well, first of all, I want to track the whole history, so I'm going to use just a Python list for this with the initial row in it, and then every time I generate a new state, I'm going to append it to this list. We're going to loop through num steps -1 times because we've already got one step being the first, the initial array, and what I want is I want to eventually have num steps in total, so I'm going to need to add num steps -1 of them. We're going to do this thing to calculate a new state and then, append that to the array. So how do we calculate the new state? Well, to implement the sort of wraparound feature, basically going to do this in 2 steps. First, I'm going to expand the state to add extra things at the end that are going to communicate the information from either side. And then I'm going to apply to each group of 3 cells, I'm going to apply the lookup table. I'm going to put these states into the lookup table to get the next version of the state in a vectorized way. And so the first step is to do that with wrapping. We're going to create an array that has the same size except 2 extra cells, and that's 1 before and 1 at the end. And then I'm going to generate that array. This is just a type annotation, but I'm going to generate that array with NumPy's pad function, which just generally takes an array and puts new cells, new entries of the array on either side. But I'm going to use this convenient wrapping mode, which is going to copy the value from the end of the array to the new space at the start, and the value from the start of the array, the old start of the array, for the new space at the end. And then using that, I'm going to do some slicing and array-based indexing in this rule table in order to get the next state. This deserves some explanation, but I think I'm going to walk through this on a whiteboard because it's a little bit easier to see. So imagine we have not 80 cells, but just 6. It would be a little bit easier for us. So here you have 1, 2, 3, 4, 5, 6 cells in our array. And imagine that this could be any arbitrary state at some point in our simulation, but just for now, let's imagine that we have black, so on, off, off. So this is our array state. What pad is going to do is going to create new cells at either end of the array and give us an array of length 8. And so let me draw those new cells. So we can have one here. Is this going to be on or off? Well, we're using the wrap mode. So I'm going to look at the end and see that this cell is off, and so this one is also going to be off. But then I'm going to look over here and also pad by 1 on this side, and this cell will be on because it will look at the value here and see that this one is already on, and so I'm going to make this one on. So that's the padding step. So far, so good. How about this indexing step? So to do that, what I want to do is basically, remember, what we're doing is we're looking for these neighborhoods of the array. So one of the neighborhoods is a sort of a slice like this. And then the first cell in that neighborhood I want to use as the first index into my lookup table. The second cell I want to use as the second index, and the third cell I want to use as the third index. And so I could do this by saying like rule table and then look up the array at this position, and then the array at this position, and then the array at this position. But what I want to do instead is notice that I'm doing the same thing for all of these positions to determine the next thing. That's what I wanted to do to get sort of the state that is going to be here. But I need a whole array of six of these cell states. And so the thing that I want to use as the first index in my lookup table is not just this position, but rather like all of the positions that are one before. So I want to say the first position for this cell should be here, and then the first position for this cell should be here, and then so on, all the way through to the first position for this cell should be this one. And so what I'm going to do is take this as a big slice. And so what would this be? This would be from 0 through to the end minus 1, minus 2, so not including minus 2, so up to but not including minus 2. And that is what I have in the code. So you can see here in the code, I have from 0 to minus 2 as what's going to go into the first part of the array. And then the next two things are just, a similar slice, but indicated, incremented by 1. And so in order to get the second thing in the second entry index into the lookup table, I'm going to want to get directly the cell like above each new cell. So that's going to be, we're going to treat that as a big slice from 1 through 2, but not including minus 1. And then likewise for the next thing, because I want what's after the cell, and this is where wrapping really comes in handy, then I'm going to want to take a slice from 2 all the way through to the end, including the last cell. So back to the code, that's exactly what I have here, from 1 through to minus 1, and from 2 through to the end. And so the first entry of the lookup, the first index into the lookup table, and the second and the third is going to give us for each entry of the new state the neighborhood that we want, and then the lookup table is going to tell us, the rule table is going to tell us what the new state should be. And so that's why this returns the thing that we take as the new state. And we're going to append that to our list and then loop again as many times as it takes. Finally, in order to just turn this from a list of arrays into a NumPy array that's about 2 dimensions, where the row dimension kind of corresponds to the step number, I'm just going to use NumPy's stack operation for that. And so this fully explains the NumPy code that we have here. And we should now be in a position to port this to JAX. But just, again, to just show you a few more times what this does, we had our version here. I can do things like I can change, what about if we wanted to look at rule 30, which is another kind of interesting rule. It's going to do the same thing, but with the different values. So we have a different binary representation. We have the sort of reverse order bits here, or the little order bits here. We have a different lookup table, and we're going to apply this update rule and get this new different simulation. Okay, so I think basically now we should be ready to take this implementation and port it from NumPy to JAX. And so, so one thing that we could do is, what I want to do is I want to take this file, this ECA0, and I want to copy that file and make a new file, ECA1, let's call it ECA1 jax.py. And so this is just going to be, our JAX version, and we're going to get rid of NumPy, and we're going to re-implement all of the things we were using NumPy for using JAX arrays instead. Oh yeah, actually, I'll create that. But before I move on to this, we also should note, because we're also interested in the performance of NumPy versus JAX. And so there'll be a lot to discuss here, but one thing I want to say first is notice that when I ran this with, it doesn't matter if I was using 100 steps or 80 steps, it was normally taking about 1 millisecond, so 1,000th of a second, in order to complete the whole simulation, including this printing out, which the printing out is not taking a long time. It maybe takes just under a millisecond without the printing, in my experience. And this is just running on my laptop CPU. I've got a M2 MacBook. Okay, so we're going to be watching that and seeing how that develops as we port to JAX. So let's do that. So let's now go into ECA1, which is our JAX implementation. And I would like to get rid of NumPy, but we'll see later we actually do need it. So I'm just going to comment that out for now. And the place we still need it is in order to save as an image, because I'm using Pillow to save an image, and that's going to expect the array to be a NumPy array rather than a JAX array. But we'll deal with that later. For now, what I can do is just get rid of NumPy and then I want to be able to still run this code. So at the moment, this is now not going to work. If I run ECA1 JAX, it's not going to work because I'm trying to use NumPy. So I want to find everywhere that I've used NumPy and use JAX instead. And so let's look for everywhere that I've used NumPy. And so NumPy, oh yeah, I have to import JAX first. So how do we import JAX? Well, to import JAX is really simple. It's just import JAX. But what we actually need at the moment is a submodule of JAX called jax.numpy. And it's typical to import that under the name either np or more commonly JNP for JAX NumPy. And so what is this JAX NumPy module? And so I can show you what that is over in the JAX documentation. So JAX has a very comprehensive and well-written documentation section, and in particular, the API reference has everything you need to know about all of the functions in JAX. And this JAX NumPy module is basically drop-in replacement for most of NumPy, most of the operations, and this documentation documents where there are slight differences in behavior and so on. But for the most part, the naming and the functionality is basically the same as the corresponding NumPy operations. So there's a very long list here. You can see this is a long list of functions. NumPy has a lot of different functions, but we can just stop at a random place and say, okay, here's a bunch of different integer types, which is one of the things we used. This is good because this is one of the things we used. In fact, the first thing we used of NumPy was this function that converts the rule from just a Python integer to a NumPy uint8. And so this was the signed integers, but I can there's also a corresponding thing for the unsigned integer. And so I can just use JNP uint8 instead, and this should take us down to the next issue. This error is no longer bothering us, and we can now proceed to the next one. And it's going to go like this basically for the next few minutes. So instead of np.unpackBits, I'm just going to use jnp_unpackBits. That should also work. Instead of np.zeros, I'm going to use jnp_zeros with dtype jnp uint8. The functionality is exactly the same, except this is going to give us a JAX array instead of a NumPy array. And JAX arrays have some slight differences that we're going to explore. But basically, the key difference is that they allow us to use, like they're the primitive that we're going to be able to use for all of the JAX function transformations and so on. So we need to be using JAX arrays instead of NumPy arrays to represent our values and do all of our computation. Okay, so I can just complete this. So there's also JNP pad, and there's also JNP stack, so that should be no problem. And now everywhere we had NumPy has been changed to JAX, except like I said before, let's just make sure that we actually say we have, in order to save as an image, which we haven't done yet, but we will do later, NumPy states is going to be np.asArray of the JAX states, which is this, and then instead of saving the data using the JAX states, we'll use the NumPy states, and then this will now work later when we need to do that. And so, but you can see every other mention of NumPy has been removed, and we just have JNP instead. So now are we ready to go? Okay, no, we still have an error. Let's explain this. This is an error that comes up quite a bit in JAX, and so it's worth getting familiar with this error message, and so that you recognize it when you see it in your code. So okay, so this is also the first of the limitations of JAX that we're going to run into. And so what's going on here? So it's pointing me to the part of the code in the simulate function where I'm trying to initialize the initial state. I'm trying to say the middle cell should be on. And so let's go to that part of the code. So here we have it. And what's it saying? JAX arrays are immutable and do not support in-place item assignment. And then it tells us what we should do instead. Okay, that's quite interesting. So yeah, this is the first of the kind of key features of JAX, how it differs from NumPy programming, is all of the arrays are immutable. And that means you can't do modifications like taking the current array and then changing one of the values. This is quite a serious restriction in terms of programming because often you might want to just change a little bit of a value in your NumPy array as you're doing some kind of iterative computation. But yeah, JAX is not going to allow this at all, at least not in the code that we write. Although we'll see later that the compiler is going to be able to take care of doing in-place operations to save time. But what we have to do instead is actually anywhere where we would be mutating an array, we have to create a new copy of the array with the modification we had in mind instead. And so JAX has an API, or like a way of doing this, that is basically the same every time. You just want to take your operation, and instead of doing an in-place update like this, it would be similar if we were doing like plus equals or something like this, any of these in-place operations, we want to replace it with something that looks like this. You want to take your existing object, and you want to do the .at method and then index into that, which sort of means, okay, go to this position in the array, and then this is going to allow you to specify a modification by using the set method. And so we want to set the value at this position to the value 1. And so this expression here is not going to do any modification of any memory. It's going to just create a new JAX array that has all the same in all of the values, so it's all zeros, except in this position where it's going to be set to 1. And so then we take that new JAX array and we just assign it to the same name as we had before, effectively overriding the old version of the array with this new copy that has the modification we had in mind. And that's exactly what this tells us to do, by the way. It says instead of array idx equals y, use array equals array at idx dot set y, or another dot at method, and then gives a helpful link to the documentation. So there are other ones, like you could add a value, you could do like the equivalent of plus equals, you could do minus equals, and so on. All of these other in-place operations, and the documentation has a full list. Okay, so in terms of performance, like I said, this is a little bit of a sacrifice in that we're sort of saying that we should make a copy when we really didn't need to do a copy. But like I said, it's going to be okay, and later we'll find out how JAX sort of handles that. Okay, so now we might be able to run our Python program. And indeed we can. So we can run through the whole thing now, ECA1 JAX instead. There's no more mentions of NumPy. Everything is being done with JAX arrays, except for the final saving as an image, if we were to try and do that. But we have the same sort of behavior as before, where we sort of convert the rule to an array of bits, and then we convert that to a lookup table using reshape. We run the simulation, and okay, it's taken a little bit longer than before, but the output is the same. So the output, this is like we saw before. So let's talk about this runtime. So okay, so this is our first time we've run a JAX program through, and we're seeing it's actually like 360 times slower than the corresponding NumPy program. So that's not a great start, but let me explain. So this should not be surprising because we've changed to using JAX arrays, but we haven't started using JAX's acceleration features at all. We haven't used compilation, which is the sort of key feature that is going to allow us to make our programs faster, and we'll do that next. But let me just explain why we're seeing this now. This is because, like I said, we've done things that have taken extra time, like copying an array instead of doing anything else. But this is just happening once at the start. This is not going to take that long. And so this is not the sort of explanation for why things are running slower overall. What's happening instead is I think these individual JAX operations are actually kind of heavier than individual NumPy operations, which individual NumPy operations are kind of heavy, but the JAX operations are sort of, there's more overhead involved in maintaining the JAX array data structure through these basic operations. Now, the thing is, when we do compilation, that's going to remove a lot of that overhead, and it's also only going to happen the first time we run a function, or like when we compile it. And then the actual code that we get is going to run very fast with even actually less overhead than NumPy, and so that's what we're looking for. And so let's now talk about compilation. Oh yeah, sorry. Also to say, another thing compilation is going to do is it's going to recognize that this copy was not necessary, and it's going to replace it with an in-place operation on the inside of the, like on the code that actually gets executed. There's not going to be any copying. But another thing is that NumPy does copying all the time when it doesn't need to. And so here's an example actually where when we pad an array in memory, when we pad an array with NumPy, we get back a copy of the array that has extra dimensions, so extra padding on either side of each dimension or whatever. Now, in principle, that doesn't have to, like that's going to involve copying all the old data from the array into the middle of the new data of the new array. But, conceptually, you don't actually need to move that data if you had set it up in mind that there was enough space to begin with for you to do the padding in memory. And so the JAX compiler is going to be able to do that kind of optimization where it recognizes, okay, this operation doesn't need to involve copying, whereas NumPy, it's just doing what you ask for every step of the way. And you can write NumPy code in a way that it's fast, but you have to be very kind of conscious about all of the copying that's going on behind the scenes. Whereas in JAX, the compiler is going to handle all of this for us. So we should be able to see actually this happen faster if we were to use the compilation feature in JAX. So that's going to be the next step. But in order to keep this for later comparison, this timing, what I'm going to do first is I'm going to copy this ECA1 JAX, and I'm going to call it ECA2, and we'll call it JIT. So JIT stands for just in time, and that's the name of the JAX function that does the compiling. So let's have a look at ECA2. So this is just the same as what we had before, but we're going to now import JAX proper, not JAX NumPy, because we're going to need to access some of the other functions. And it's common to basically import JAX like this, to import JAX and then import JAX NumPy with like a little shortcut, because we're often using that. But everything else we're just going to access through the top level JAX library. So how do we do just-in-time compilation? Well, it's actually pretty simple. Let's do it inside the performance counter. Oh, actually, I guess we might want to time the compilation and then the execution separately. So let me just make the code a little bit more complicated here. I'm going to take this timing block and duplicate it, and then say compilation complete. And then in here, instead of doing the execution, I'm just going to compile the function. So how would we do that? So I'm going to say I have a compiled simulator, and I'm going to call jax.jit on the, oh, sorry, not simulator, I guess I should call it simulate, on the simulate function. And so the first thing to notice about this is that what we actually have is a very simple API of any Python function can be compiled as long as it meets the assumptions of JAX, and there's a few of those that we'll discuss in detail throughout the course. But today it's going to be like just this Python function is going to be fine. So we can compile it, and then we just do that by just passing it to this function. So this is a function transformation. It's going to take the simulate function and return us another function, another Python function is going to be the compiled version of the simulate function. And so this is going to be called compiled simulate. And then I'm going to call compiled simulate instead. I don't think this is going to work. So one of the things we need for our functions to compile them is they need to be pure functions. And we'll talk about why this is the case later. But basically, that means pure functions means there could be no side effects. And one classic example of a side effect in Python is a function that prints something to stand it out. And so that affects the state of the file system by writing to a file, or of the file anyway. And so I'm just going to comment out all of the printing that was going on inside this simulate, and then this should work. However, I don't know if we're going to see what we expect. So let me see. Let me just see what we do see. So we'll just run Python ECA2 JIT, and we'll see what happens. Oh yeah, okay. I forgot about this actually. This is a common error, so I'll mention this. So so when you compile a function, it's important that JAX knows exactly what shapes all of the arrays are going to be during the computation of the function. And in this case, we have a function where the shapes depend on the inputs. And so they depend on the width of the num steps, because the num steps is going to determine how many things we're stacking together here. And the this result, this output type, is going to depend on num steps. And the width determines the step of the individual arrays, the size of the individual arrays. So what that means is, in order to compile, I just have to basically tell JAX, I have to tell it, you're going to compile this simulate function, and there are going to be some arguments that I want to be called static. So they should be known at compile time. And then you don't have to make the same computational graph for all of the possible values of these inputs. You can just make a different computational graph depending on the value of these inputs. So I'm going to do that by saying static argnames is a list, and I'm going to say the argument width and the argument num steps are going to be the arguments that should be static. And this basically comes up in the error. So shapes must be a one-day sequence of concrete values of integer type got JIT tracer. That's a little bit incomprehensible, but But what it tells us to do is use static argnums. Actually, static argnums is an alternative to static argnames where you give the positional IDs. So this would be argument 0 is rule, argument 1 is width, and argument 2 is numstep. So I just say static argnums equals 1, 2. But here I've given the names because I find that a little bit more readable and then robust to if I change the position, and it'll also give me a helpful error if I change the name. If I add a new function argument, but I forget to change the compilation, it will tell me with an error. So I prefer to use argnames. Anyway, so now we should be able to run this, but we don't get what we expected. So okay, let's compare to previously. Previously, it took us 0.36 seconds to run the whole thing with JAX, which was like a lot slower than the NumPy. Now, after we fix the error, it's compiling is almost immediate, but it takes us even longer, 0.55 seconds to run the code. So something must be wrong. And indeed, this I have not been completely transparent with you. This compiled simulate. Oh yeah, this is because the best way to understand this is because it's called just-in-time compilation. This doesn't actually do the compilation. It just gives us a version of the function that every time you call it, the first time you call it, if it needs to be compiled, it will then compile the function. So the compiling is actually not happening until the second time, or the second timing block here. And so the way to fix this, the basic way to fix this is to call the function once if you want to time how long it's going to take to compile it. And this is actually the time it takes to compile the function, not the time it takes to execute. Okay, so let me run again. And what I've done in the code is I've changed it so that we now compile, simulate, we run the JIT command, and then we call the function once, and we get this value, which we're not going to use. And then we're going to say that's the time it took to complete the compilation. And then we're going to go again, we're going to call the function a second time, and it's going to tell us how long it takes to compute the value of the function. But this is actually also, this is extremely fast, and indeed, this is a little bit dishonest. There is another missing piece, which is that we need to make sure this code is actually happening now and isn't going to be like, this value of this JAX array isn't going to be like populated later. Sometimes JAX does some kind of cheeky, lazy evaluation like that. And so the best way to ensure this for profiling purposes is to take the JAX array that we get out of this and use the block until ready command to make sure that we actually have this value fully computed before we move on from this line. And that is going to give us an honest version of this timing comparison. So I'll do that, run that now. And now we see a real answer. This is a reliable timing. So it took us 0.58 seconds to compile the function, and it took us a fraction of a millisecond, so 3 zeros, whereas with NumPy we only had 2 zeros, to actually evaluate the function once we'd compiled it. So finally, we've got some benefit from using JAX. And this is basically, this is our first example of something happening faster with JAX, if you don't count the compile time. And the argument for this is that, okay, if you are, well, first of all, the compile time is not going to scale with the sizes of the arrays. It's going to be just as easy for JAX to compile a large thing, whereas it might take longer to execute the larger version of the function. And the second thing is, maybe we're going to be able to call this multiple times. We already saw that calling it multiple times here. Technically speaking, this like fraction of a millisecond was also included in the first time we ran, and included in the compilation time, by the way. But anyway, if we were to call this 1,000 times, it's only going to need to be compiled once. And so this compilation time can be kind of amortized over every time you call the function. And so that could be better than if you were, even though it's individually faster to run the program with NumPy than with JAX if you include compiling. To run the program 1,000 times, it's going to be faster with JAX. Actually, I guess 1,000 times, yeah, because it was 1 millisecond. So if we ran it 1,000 times, it would take about a second with NumPy. And here, it's going to take, 0.6 seconds to compile, and then another 0.1 seconds to run 1,000 times this. And so 0.7 seconds total. So actually that is not just saying 1,000 times is some big number. Actually, technically, if you did the calculation and if we did the performance, I'm confident that we would see the JAX solution then overall faster. Another thing, so we could do that. I don't want to change the code too much, get it a bit complicated to time things happening 1,000 times. But another thing we could do is we could just run a much larger set of arrays and see if we get another performance difference. So if I take NumPy and I say, let's make the width, instead of 80, let's make the width 8,000. And let's make the num steps also 8,000. So now I'm going to create an 8,000 by 8,000 array. And then I want to, okay, I can't print out the result of this because it would just take too much space on my terminal and it would take forever to print 8,000 lines. So what I'm going to do is I'm going to say no print image, because we have this print image command. So I'm going to turn off printing the image so that it doesn't print the image at the end. And then I do want to actually see the output, so I better turn on save image. And then it will save to a file called output.png. So I run this, takes still less than a second, but 0.78 seconds, and renders to output.png. Okay, so then I can look at output.png. It's going to take a moment to load, but you can see this is a really big version of what we're seeing here. It's actually a little bit big and making preview sort of a little bit erratic, but I think if I full screen, I should be able to zoom in here. And you can see the sort of general pattern of the rule 110. And then at a big scale, it's going to do this thing with wraparound, 8,000 rows. So this is like a much bigger version. Okay, and then, so let me close this. And then let me do the same thing, but with ECA2JIT. So it would probably take a while longer, even if we did it with ECA1 JAX, but we know that's not the real test. We want to compile our code. And so let's see this. Okay, something's taking a while here. And actually, we're going to fix this next. At the moment, the compilation of this 8,000 step version of the function is going to take quite a long time, maybe like 30 seconds. So let's just wait for that to run. And I'll explain why in a moment. But what I want to watch for is the time that it takes to actually run the computation. So the NumPy computation took 0.78 seconds. And let's just wait and see what the JAX thing does once it eventually finishes compiling. I guess while we wait, I'm not 100% sure how long it's going to take. I should explain why it's taking so long. So what's going on here is that basically how JAX compiles is it runs a version of your function with some abstract arrays instead of real arrays. And these abstract arrays track all the operations that they've been through. And when you return an abstract array in the end, it basically represents a computational graph of all of the abstract arrays and computations that happened on that array to get the final value. And so you can, yeah, that's a computational graph like you might have in PyTorch or whatever. And JAX builds them by running through your function with these abstract inputs. Now, if you look closely at our function, it involves doing this sequence of operations several times, 8,000 times, or one less than 8,000 times in this example. And there's a pad operation and then a lookup in the rule table, a bunch of slices going on. So this is actually going to be an extremely long computational graph. And then that computational graph is given to the compiler, and it's going to have to compile a very long program. Oh no, okay. So yeah, okay. So it took actually a while, but I realized that I had a mistake because I deleted the NumPy import. So I better bring that back so that I can actually save the image. You can see we're using it. We're using it here. My bad. Sorry about that. We can run this again. It'll take another minute and a half, but I'll keep explaining what's going on. So yeah, so back here. So imagine we've built our computational graph with 7,999 versions of these pad, slice, and lookup in rule table operations. And we're building this huge computational graph, and then everything in that computational graph is given to the compiler, and it has a lot to work with. And now, there's a lot of structure to this computational graph, but we haven't told the compiler about that structure. So from the compiler's perspective, it's just given this huge sort of graph of operations, and it has to process it. And that is what's taking the time. That's what's taking, about 100 seconds to handle. And so if we wait for that to work, we'll see that it took. Oh, okay, that's okay. This was only a problem in actually saving the image, so we can already look at the timing. It took 97 seconds to compile that huge computational graph, but once we'd eventually compiled it, it only took 0.088 seconds to actually run the computation itself. even though we were using arrays of much larger than before. And so compared to the NumPy, that's like nearly 10 times faster. So that's pretty neat. We were again sort of having a 10 times speed up, I guess, initially when we went from about 1 millisecond to about 1/10 of a millisecond. So if you're not including the computation time, which yes, here is horrendous, this is another similar sort of 10 times speed up. Okay, what about this compilation time? So how can we make it so that, yeah, here we go, another 100 seconds, another nearly 10 times speed up, and now we've put this in output. So this is going to look exactly the same as before, but this time it was computed with JAX. Okay, so let's just move on. So what I want to do next is solve this problem of the really long compile time for a very large loop. And so I can create a new file. So let's copy ECA to JIT and call it ECA3. I'm going to call it scan, because scan is the name of the function that we're going to use in order to save ourselves here. Now, scan is a function that is basically a JAX version, a JAX function that says, okay, take this function and do it, 8,000 times. And then the computational graph just has this very simple function in it that has the one version of the pad and the slices and the rule table lookup and so on. And JAX just sees, I want to do that 8,000 times. And that's much easier to compile because it only has to think about the actual inside of the loop once. Rather than doing it so many times. So in order to use scan, we have to get rid of this for loop. We basically want to call this, we call this function jax.lax.scan. We'll see later sort of what lax is. We're going to pass it, it's going to take a few arguments. One of them is going to be some function, I'm just writing some pseudocode here, some function that corresponds to one step, and then the initial input, and then let me call this initial thing that's called a carry, and then the number of iterations, which I can say right now is num steps minus 1. And then that is going to return what's called the final carry and the outputs, which is going to be our sort of next states. Okay, so let me explain a little bit and fill in some of these blanks that I've left as sort of things. So I want a function called step, which is going to compute a single step of this loop. And I basically want to take what's inside this function, this loop, and put it inside the step function. But scan is expecting this function to have a specific input type. And the input type is what's called a carry and then an input, which I can't call input because of syntax highlighting. Oh, actually, I guess I can. And then output is going to be a new carry and an output. I won't type annotate it because these can have sort of any types. But I guess I could say it's going to output a tuple. It's going to be a new carry and an output. So what's a carry? So a carry is a part of the computation that comes in at the start and then is like computed within this step and is then passed into the next iteration of the loop. So the obvious thing to use for the carry here is going to be the state itself. So actually, I'm just going to call this excuse me. Actually, I'm just going to call this state instead of carry. And we're not going to use the input for this because there's no thing that this would be like a loop variable like this time variable or something like that we determine up front, and each step of the loop, this variable comes into the loop. But we don't have anything we're not using this time variable. So let's just ignore that input. And then what we want to do is we want to compute this state wrapped with the current state. And then we want to compute this next copy of the state. I'm going to just call that next state, just to be clear, but it's the same as before. And then I said we have to return a new carry, so that's going to be the next state. That's going to become the state argument in the next call of the step function. And then we also have to return some output, and the output is going to be given to us at the end in this jax.lax.scan is going to return the final carry, which is the next state that comes out of the last step. And it's going to return all of the outputs that have happened from each step, all in one big array, which is what we want. So that I'm going to actually output the next state as well. And then this array that we get output will be 7,999 by 8,000, the width array that has at each row one of the next states that we computed at one of the steps. So I'm going to return next state twice, and it looks a bit funny, but that's just because that's what we need for lax. And so I'm not going to use this final carry. That would just be another copy of the final row of the next states row in this case. The function is going to be this step function, and the initial carry, which is the initial input to the first sort of way through the loop, is going to be our state that we computed up here, our initial state. So I'm going to put in state. You know what, just to be clear, I'm going to call that initial state, and I better change it up here as well. So this will be called initial state. And okay, so this is now the JAX version of my loop. Except instead of a list of states, we've got now, instead of constructing this list of states, we've got an array of almost all of the states. This is, the 7,999 rows, and we have initial state, which is corresponding to this first row. So instead of stack, I'm going to want to concatenate those. So I want to concatenate. Concatenate takes a list of things to concatenate, and I want to concatenate the initial state with these next states. But this is not going to work quite because the rows, this is just a single row, and this is like a matrix of rows. And so I want to make sure that this is going to have the right shape. I need it to have an extra dimension, and so I'm just going to use none, or the equivalent to np.newAxis, or in this case I guess it would actually be jnp.newAxis. And so this will turn this from a length 80 or like a length width, or for example a length 8,000 vector to a 1 by 8,000 array, and that is going to be able to concatenate this along the 0th axis, which is like the row axis. And so now this should conform to our type that we wanted out of num steps times width of a uint8 array. And so this version should be much faster, even if we're dealing with very large, even if we're dealing with a very large number of iterations. So let's see. Okay, I've got some problem. Oh, of course, I forgot one version of the initial state. That's what happens when you're not careful when you're renaming. So yeah, now there we go. Look at that. Okay, so it takes about as long as before to actually execute. Actually, I guess it's taking a little longer. It's taking longer, at least in this case. I'm not exactly sure. The compilation time was much faster though. Instead of 97 seconds, it's taking a fraction of a second. So, problem solved basically. And the code got a little bit more complicated, but once you've written a few of these scans, let me tell you, they become very natural, and you can do even more complex stuff like using the inputs and using sort of multiple different things as your carry. You can use a tuple of things as the carry. It becomes very straightforward to and very easy to get used to. So, and we've got the whole course to figure out how to get used to that. Okay, so what we're up to, let's just review for a second. So we've introduced this elementary cellular automaton simulator. We ran through it and sort of saw all of these NumPy operations. We've replaced all of the NumPy operations with JAX versions, and we saw that just naively that took a little bit longer. But then we learned how just-in-time compile the whole program, and then it ran actually faster if you don't include the compile time. And now we're at the point where we can compile and run. If you look at this, we compiled and then ran this program. And if we were to compare this to the NumPy version, which I can't remember exactly how long it took, I guess it was like some other fraction of a second, sorry, just over a second or so. Almost a full second, that's right. And here we took a total of about 0.21 seconds or something like that. Or 22. So we're overall faster for large enough inputs, and that is pretty cool. So we were able to just change very minimal stuff about our code, including taking a little bit of extra care with this long loop to make sure the computational graph isn't too big. And then JAX was able to compile and run the function before NumPy even finished running it itself. So that's pretty cool, and that sort of shows the potential of JAX for accelerating our array programming. So we're nearly at the end of the lecture and the material that I wanted to discuss today. But I want to show you one more really cool thing that you can do with JAX once you have a function that is written in this way that it can be like using JAX arrays instead of NumPy arrays. And that's called vmapping. And so let me just create one more version of our function. I want to call this ECA4 vmap.py, and then I want to go into ECA4.vmap, and I want to do something really crazy. So in array programming, all the time we have to deal with like arrays of data, and we want to put them into our functions, and we want to have those functions be vectorized and kind of operating on all of the like loops that we want. We want them to be happening kind of in a sense inside NumPy, or inside JAX in this case. Excuse me. And so vectorizing things is very important. If you know NumPy programming, you know how important this is. Now in this case, JAX allows us to do even more flexible array programming and vectorization in the following way. So we can have this simulator that takes a single rule and computes the sort of history of those states. But what we can do is we can say, what if I wanted to give it a vector of rules? One way to do this in Python would just be to say, okay, if I have a list of rules, I can just run this function once. I can have a for loop and go through the list of rules. And for each rule, I can call this function. And it would be pretty fast because it's in JAX. But we've got a loop again in our Python code, and we know that we like to vectorize things. It would be nice if we could run our program on all of the rules kind of at once or in parallel. So you could go to your simulate function, and you might have done this with NumPy code before, where this happens all the time, for example, with batching inputs for neural networks. If you want to run your forward pass on a batch, then you need to kind of have this extra batch dimension. You need to make sure all of the operations you do, you take care to manage, which axis is the batch dimension, and make sure that there's no interference between the batches, and all of your code is kind of executing in the right place, and the matrix multiplications are lined up. In this case, we'd have to make sure, I think most of these operations would be fine. We could just add a batch dimension to the state, and then we could make sure that we set all of the width to 0, or maybe we could do this with the same initial state and do some broadcasting, whatever. But it can be very tedious to go through your code and make sure that everything is lined up. JAX is very cool in that it has this function called vmap, for vectorized map, that can take a list of inputs, or an array of inputs, and a computational graph, and go through that computational graph for each sort of value along an axis. Basically, it's automatically adding a batch direction. And so the way this looks is as follows. We go back to the point where we were compiling our code, and instead of just compiling simulate, we get a vectorized simulate first with this function jax.vmap. It's another one of these function transformations. So it's going to take the simulate function as an input. We need to tell it a little bit more about it. We need to tell it, for example, that the first the first input is the one we want to vectorize along, and we want to have an axis 0 that will correspond. This is our rule, remember, this first input. And we want to have, for that input, we want to have an array where axis 0 is like all the different values that you should be doing as like a batch dimension. Basically, axis 0 of this array is going to be the batch dimension. And then we don't have a batch dimension for the other two inputs. The width and the num steps are just going to be one value for all of the different things. And then we tell it the out axis. This is actually the default. We don't have to specify, but we also want to get out an array where there's an extra dimension, and it's the 0th dimension that corresponds to this input batch dimension. So we'd have this like 2D array come back, and it would become a 3D array where the first dimension or the 0th dimension corresponds to which rule we were talking about from our vector of rules, our array of rules that we put in. And so this is going to give us this is a function transformation. It's going to take our function and give us a new version of the function that is has been transformed in this way to take a different type of input. And so I can compile that instead, vectorize simulate. And so now this compiled is actually compiled and vectorized. And then, well, one thing that happens with vmap is that you can no longer refer to these arguments by name. You have to use positional arguments instead, which I'm not a big fan of, but it's not too bad. But instead of a rule, we can't give a rule anymore. We have to give an array of rules. And why don't we just give all the possible rules just to see what this is capable of? So how we would do that is we would say jnp.arange 256. Remember, the rules is like an 8-bit integer. And so there's 256 possibilities, 0 through 255. And arange in NumPy would give us a vector of integers, 0 through to 1 before the length. And there's just a JAX version of that function. So this gives us just a uint8, actually I think it will be an int array with 0 through to 255 inclusive. And so that's exactly what we need. But now we can run the simulation on all of those rules at once. And then we better make sure we do the same thing here. Remember, this was just the time we called the function in order to make sure that it's compiled actually properly so that we're only timing the version that we actually want to run. I think I might have figured out why, just pause for a second. I think I might have figured out why earlier this compilation was actually happening faster than the overall simulation. I think it's probably because I forgot to block this one until ready. And so it might have been doing some lazy shenanigans here. But even if it had taken this long plus this long, it still would have been faster than NumPy overall. So that's good to see. But sorry about forgetting that earlier. Anyway, so now we've got our compiled and vectorized simulate, and we should be calling it with all possible rules at once. Now, we couldn't possibly print this out. First of all, this is no longer a single image, it's an array of images. Well, okay, I guess we can try. We don't have to do 8,000. We can try for rule state in, this states thing is no longer just states. This used to be a width by num steps array. Now it's a num rules by width by num steps array. So I'm going to call it something else like, I don't know, stateses. Or there's this convention I saw where I guess you would say you would have an R dimension and then a time dimension and then a state dimension after rule. So this is states RTS. And then I'm going to say for states TS without the rule in states RTS, I want to print out states TS. And this is going to go really fast, so I might just delay it here so that it doesn't look crazy. And I'll maybe just sleep for like 0.5 seconds between things or something like that. Okay, so I think I could already run this, making sure not to do 8,000, but just the original vmap thing, and this should work. And you can see it's going to start flicking through these different rules. Each rule has a different history that it builds. And you can see they all start with the same thing, but then afterwards you see something different happening. So I'll leave that running. It might run through. It would be nice to see all of these at once. And so what I'm going to do is use this other cool library called inops, which I don't think I've imported. But it's in the virtual environment if we installed the requirements properly. So if I import inops, that's going to allow me to use a very sort of intuitive notation in order to create a version of this array that is, instead of being 3-dimensional, is going to be 2-dimensional, where all of these images are arranged in a grid. I guess I need a 16 by 16 grid for all 256 rules. So let's do that. So this will be, let's call it states in grid equals inops.rearrange, and we'll give it the states RTS as input. And then I'm going to have to describe the reshaping operation that I want to do. So we currently have like a rule, time, state dimensions, and we want to have 2 dimensions. What I want to do is I want to take this rule dimension and call it rule H, rule W. And then I want to distribute those, and basically this will split it into a grid where I'm going to say that rule H is going to be of size 16 and rule W is also going to be of size 16. So this is going to turn that first dimension of 256 into a 16 by 16 thing. And then I want to take the first of those dimensions and distribute it along the time axis, or distribute it along with the time axis along the first array of my output. And then I want to take the width and share that with the with the state dimension. So I could have also called this num steps and width. So I'm going to have 16 by num steps be the height of my image, and 16 by width be the width of my image. And so now this state's grid should be a JAX array, and we'll have to convert it to just in time. We finished going through all 256 things. So this will be NumPy states grid. And then NumPy states grid is the thing that we want to save as output. And so now let me say no print image, please, but yes, save image. And I must have forgotten something. Oh yeah, of course, I need to put a comma there. My bad. Output.png. Again, I guess we didn't look at the times before, but compilation was like lightning fast. This is now including the first time we executed the function. It looks like it took a little bit of extra time to vmap. And then the simulation was lightning fast again. I guess this is representing 256 times. It's faster. Okay, so interestingly, so I think before, when we were running the smaller arrays, to run a single one of them was taking 1/10 of a millisecond. So there was a 1 here. This is taking 45 times longer to do 256 times the amount of computation. So it must be leveraging the parallel. I must have had extra processing power in parallel on my CPU in order to achieve that speed up, and it's been able to take advantage of that. But it's not happening, it's not happening like all instantly. It's not doing all 256 runs all at once. But yeah, it's quite interesting that it's still faster than 256 times, which is how long it would take you to do this with a for loop. So vectorization is giving us a bit of a boost here. Okay, but anyway, let's have a look at this output. There we go. Okay, so this is what we wanted. So here we have, arranged in a 16 by 16 grid, the state histories from the initial sort of configuration of a width 80 state with the middle cell, or approximately the middle cell on. And each of these corresponds to an 80 by 80 sub-image that represents that state history. So here we have that initial state, and then this update rule means that obviously all of these 3s turn on, and then when there's this thing, it gives us like a tilted version of Sierpinski's triangle coming out. Okay, and then let's see if we can find rule 110. So in this 16 by 16 grid, we have, I guess 128 would be here. So this would be 100 and, actually I guess this would be 127. 16 before that would be 111. And so this must be rule 110. And there we go. There's our familiar pattern that we started with. But you can see the point is all of these at once. And so that is pretty cool. And so I guess that basically concludes the demonstration for today. I just want to leave you with the challenge for this week. So each week, or each lecture, is going to have a challenge built in where it's a chance for you to take what you've learned and do something more with it, where you have to figure out on your own exactly what it's going to look like and how to do it. And this might involve looking through more JAX documentation, playing around with things yourself. And this is, so the sort of topic of this lecture has been all about introduction to JAX NumPy and first look at these function transformations. And we're going to do a lot more detail on these function transformations later. But to give you a chance to play around with JAX NumPy, I think it'd be fun to, instead of implementing an elementary cellular automaton, what if we looked up Conway's Game of Life? There we are, Conway's Game of Life. So you might have seen this before. This is a two-dimensional cellular automaton. And so instead of showing a history as a grid, you show a history as a GIF, as an animation. So you have your 2D state, and then in time you represent the sort of evolution of the system, which I guess is actually more natural than using time as a spatial axis. But anyway, you can look up the lookup table that corresponds to this automaton, and you could maybe implement that lookup table yourself as a JAX array, and then you could implement your own simulator. You might like to do this in NumPy first, and then port it to JAX and see if there are any differences. I wouldn't worry too much about compiling it. It's okay if it doesn't run too fast. We'll learn more about compiling later in the course. But for now, yeah, just have a play with JAX NumPy versus NumPy and see if you can implement this more complex automaton simulator. And so I'll leave you with that. Have fun, and I'll see you next time.